All right. Welcome, everybody, back to the Allen School. Our first time together in almost 2 years. Super, super excited to have everybody here. Woo! It is absolutely delightful to see all of your shining faces. We also have a bunch of people joining us in TV land, so welcome to all of you as well. So glad everyone could be here. Really, really great to come back together. Today we have a treat especial. The Pulse Group, PLSE, which expands to programming languages and software engineering, is going to share some of the work that's been going on in the group recently from senior students. So, broadly, we cover lots of topics. This is only a small sampling, but if you're interested in anything from type theory to thinking about 3D printing as compilation to how to design and implement tests, we got a little bit of everything. A lot of emphasis on verification and synthesis. So it's just a small smattering, but please feel free to come by the lab anytime and visit us. And make sure to pipe up with questions during the talks. That's one of the great joys of being in person. I'll be monitoring the Zoom chat, and we'll interrupt speakers with questions, or we can wait till the end. But I think with that, we'll go ahead and kick things off with Remy, our first speaker, telling us about new perspectives on relational databases.
Hey, thank you, Zach. Thank you, everybody, for being here. Okay, trying to test. All right, so today we've got a pretty diverse audience, so I'm gonna try to keep things simple. And then I'll start by taking a very quick crash course on databases. So what is a database? And here we have this stereotypical picture we have of a database. So here we have a table. Database can have multiple tables, but today let's just look at one at a time. So here we have a table, and it's probably in the database of some kind of animal shelter, a cat shelter. So these are real cats in our department, and then in your defense, you'll be required to identify each of them. So you really need to pay attention today. So each table consists of several named columns. Here we have 4 columns. We have the name of each cat. We have the biological sex of each cat. We have color and age. And then it also has a bunch of rows, and every row contains a value for each column. So possibly we have missing values. You see that Betty is a very mysterious cat. We don't know how old she is. All right, so if we don't have duplicated rows, here we have each row is unique, then we call this is the set semantics. The table is a set of rows. However, it's okay to have duplications. So if we do have this, it doesn't have to be immediately duplicated. If we do have duplicates, then this is called back semantics. So instead of a set of rows, we have kind of a backup rows where we can have copies. Right. So the first operation we're gonna look at is join. So this puts 2 tables together and then produces a new output table. So the way this works is that first we'll notice that the output table has 5 columns. And then these are created by combining the unique columns from the input tables. So we see the first columns are from the first table, and then the last column, which is a new one, is from the second table about the origin of the cats. All right. So this is called a schema. So the names of the columns are called a schema of the database. And then the way we're going to combine these tables is by doing this. So we'll look at the first row. We'll look at each row starting at the first row. And we go to the other table and then look for rows that have matching name with our row from the first table. And then we put together all the values to create the first row in the output. Right? And then we repeat, go to the second row, we find another match, and then this creates another new row in the output. And so on and so forth, right? So we didn't find a match for Betty, and then now we have a match for Zoe from Philadelphia. So that's join. And then the second way to combine tables is called union. And then notice here that the 2 tables we're going to take union off share the same exact column names. So they share the same exact schemas, and this is required if you want to union 2 tables together. And union is really simple. What we do is really just take all the rows from each table and then put them together. So here we see that the first table provides 2 rows, second table provides 2 rows, and the output table contains all 4 rows from each table. Okay. And then the last one is a little bit more complicated. So we have this aggregation operation, which needs to specify 2 types of columns. So one is called the group by column, and then the other one is called the aggregate column. So the way this works is that, so here we look at 1 column for each type, and then we're going to take the group by column, which is biological sex, and then we have all the values in our input table, we copy over to the output table. And then we're going to run the aggregate operation, which in this case is minimum, on the aggregate column. So here we see that we only have 1 single male cat, which is Casa, 4 years old. So the minimum is 4, and then we have 2 female cats we know the age of. So minimum is 2. Right. Okay. So all the examples so far we've seen don't contain duplicates, and the output table also doesn't contain duplicates. So what happens if we are talking about batch semantics, which means that we have duplicates in the tables? Right. So the duplicates might be caused by different reasons. Maybe there's a mistake in data, when we wrote down the tables, and maybe there are just copies of the there are just 2 cats of the same name, both from say Seattle, called Casa, and that's entirely possible. So we don't care about the reason why there are duplicates, but what we need to do is to preserve these duplicates in a reasonable way. So the way drawing works on duplicates is really simple. So we don't need to do any special handling. So we're just going to pretend that each duplicate is a different row. So as we did before, we're going to start from the first row. We see Casa male orange 4, and then we go find matching rows from the second table. Right. So we have 2 matches where the name is Casa. So this will contribute to 2 of the first rows in the output database because we have 2 matches. Right. And then when we go to the second row of Casa in the input table, the first input table, we'll once again find 2 matching tables in the other table, and this also contributes 2 copies of the record. Right. So at this point, you might have noticed a pattern. So we have 2 copies of the same row in the first table and 2 copies of the same row in the second table, and then our output contains 4 copies. So 2 by 2 is 4. Right. So that's a great intuition. So actually, if we look at the tables from a different perspective, that's the kind of formal way to understand this intuition. So the way to look at it is that we try to understand each table as defining a function. So the function will map each row to the count of appearance of this row. So for example, if we use function f to mean the first table, then we say that this f function will map Casa male orange 4 to a count of 2. And similarly for the other table, the function g maps Casa and Seattle to a count of 2. And then in the output table, we'll have the function h mapping the output row to a count of 4. Right. And then drawing becomes a very simple operation we're all familiar with. It's simply multiplication. Right. So if we look at the output table for any row of these variables, we simply multiply the count that we get from each input tables. Yeah. So popping up at a high level, we see that each table is a function. So by changing the output type of this function, we can very elegantly map into different semantics we talk about. So just now we see that the output type is integer, and then that corresponds to batch semantics where we handle duplicates. And then if it's a Boolean, so that will map to set semantics where we deduplicate the records. And then even more, so if we map it to real numbers, we can get some sort of a probabilistic semantics. So when we're unsure about the occurrence of a record in the database, we can have assign a probability of its presence. Right. So formally, this is called a summary ring. So algebraically, this is called a summary ring. And then it comes up with D, which is the domain type. We have Boolean integer real, and then two operations, which is the generalization of union and join. So the plus is union times is join, and then 0, 1 are identities that are helpful. Right. So for our case, the set semantics correspond to the Boolean summary ring, and then our best semantics really correspond to natural number summary ring because we cannot have negative counts. Right. And then here are what the operations correspond to, so you don't have to look into much detail. Yeah. And then, so if we extend the summary into other more complicated ones, this gives a really powerful expressiveness. So we can do some kind of probabilistic programming using real numbers. And then we have this really exotic tropical summary ring that allows us to express even shortest path computation. Yeah. So what is the point of doing this? So this is kind of a abstract theory mumbo jumbo. So first of all, this is a very elegant framework to unify different semantics of our databases. And then once we have this really clean unification, we can discover new semantics for databases by instantiating a framework. And then this will allow us to express new types of computation. For example, we can do shortest path. And then what's also important is that this enables algebraic reasoning about databases. So what I mean is that because we use this really well understood operations from summary rings, we can take advantage of the associativity, commutativity, and distributivity of the operations to reason about database operations. And this kind of leads to really powerful query optimizations where we rewrite the query to make it faster. And then we can also leverage standard automated reasoning tools. So well-known one are called SMT solvers. And then we can just use standard functions to model databases. And then we also use standard theories, for example, linear integer arithmetics, to model the operations and then reason about them. Yeah. So today I just showed one of these perspectives. There are many other perspectives from which we can look at databases. So there's a physical one, logical one. We can look at database as a graph, hypergraph, and then we can also look at it as a hyperspace. So I think my takeaway from this perspective is that it's really powerful to look at a concept from different angles. And there's one of my favorite quotes, which is saying that when we do math, the point is not trying to come up with a really complicated proof. It's trying to paint a landscape from which the proof is obvious. And then switching between different perspectives might help us to find this perfect landscape. Thank you.
Many thanks, Remy. And we can take questions from the audience as well. I have the Zoom chat open here. Jasper, if you want to go ahead and set up so we can do a smooth transition. But yeah, so one thing I was curious about, Remy, what if I want to use different semantics at the same time? Can I combine, can I decompose a query to be partially under probabilistic semantics and then also partly under bag semantics? What's an example of that?
That's probably new research. I actually haven't seen
okay.
So you will need
see
to
this the colloquium. You should come. You'll get research ideas. This is you're seeing it live, folks.
Yeah, we can have a combination of combinatorial papers out of this. Yeah, but you'll have to make up a summary ring using this framework. So you want to put two summaries together and then make up a new one. Yeah.
Max Bilsey.
So for the Boolean semi-ring and probably integer semi-ring, we have great implementations. Those are like your standard databases off the shelf.
Yeah.
What other semi-rings have you implemented, or would there be maybe good implementations for?
Yeah. So if you think about real numbers, actual real numbers, we have many systems implemented. So say TensorFlow. So if you have real numbers, a table is a tensor, so they are exactly equivalent. So this is just one way to look at this kind of implementations. So many of these are implemented, and also shortest path. There are shortest path algorithms, and we can understand them from this perspective. Yeah.
Can you give a couple of samples of what applications this could have?
Yeah, so...
And remember, you might repeat the question for the Zoom folks as well.
Okay, yeah, so the question is what kind of applications this can have. So, so one of the applications, so one of the projects I was working on is trying to optimize tensor programs. And then, so essentially I was able to use these really simple identities to rewrite a tensor program to make it faster. And then these are more finer grained than your standard matrix multiply, which is not commutative. And then we can break it down and then discover more rewrites. So that's one of them.
Is that because you see the tensor product as each matrix as a database and you combine them, or?
Yeah, so you can view them as functions, which are databases. Yep.
Thank you.
All right, let's thank Remy once more. Okay, up next we have a great treat. Jasper is sort of really pushing the notion of what objects are within Pulse. So, I heard he worked with objects, but it actually means physical objects in the real world. But he puts them in the computer and does cool stuff and thinks about how you can also make machines to make objects. So there's a level of meta, which is why his work with Nadia fits right in. So please take it away, Jasper.
Yeah. Thanks, Zach. Hi, everyone. My name is Jasper, and this is work I did with my colleagues Chandra and Kang, and with my advisor, Nadia Peak. And I'll be talking to you about why making physical stuff with computer-controlled machines can be surprisingly frustrating, and how we can help makers out by using the same computer-supported reasoning that lets programmers work quickly and accurately. So digital fabrication machines use computer programs to make physical objects. For example, in the case of a 3D printer, you would want to model what you want to make in 3D, and then you translate the model's geometry into the path that the 3D printer head takes. Then you translate the tool paths into machine instructions, kind of like assembly code, and then send them to the machine, and then you get some sort of physical product, here a plastic Pikachu. And so there's all sorts of fun research going on at all stages of this pipeline, both in computer science and in other disciplines. But despite all this work to optimize different parts of the process, when we zoom out, every maker has to answer the fundamental question, given what I want to make, which machines will I need to use and how do I use them? And long story short, we still don't have a concise way to answer this question. For example, consider 3 off-the-shelf 3D printers. There are probably some of these around here. You can buy them. Before a maker can start making anything, they need to know how they're going to fabricate their design. For example, the Pikachu again, and particularly in the case of larger prints, a natural question is this printer, can it fit the model that I want to print at all, or is it too small? And questions also arise after selecting a machine. So if you consider this open source pick and place machine, it precisely places these like tiny SMD components onto a printed circuit board using, very precisely using several needles with different sizes, right here. And to use this machine properly, we need to enforce the condition that before picking up any component, we must have equipped the needle that is designed to pick up the components of exactly that size. So where's the manual? If a maker doesn't already have personal experience with how to select or use a machine for a given task, then the resources that can help them are quite scattered. So this might include material sheets, these tips hidden in the depths of online forums, sites for looking up debugging problems, if some of you have seen this particular website, community wikis, or hardware data sheets, and also community wikis. And so these are all great, but it's an awful lot of work not only to find all this information, but also to know how to even interpret it and apply it to what you're doing. And it would be very helpful if we could distill some of this informal knowledge to a more accessible and reproducible form. And this leads us to ask, how can we formalize knowledge about when and how we use machines? And to do this, we built Taxon, which is a language that encodes machines, workflows, and what we call rules of thumb as actual programs. And so Taxon applies the safety and extensibility of programming to hands-on making. So we implemented Taxon in a web interface where makers can browse a database of machines that are represented programmatically as what we call these machine plans right here. And these are loaded into the scene, which is a physical simulation, a simulation of the physical version of the machine. And here we've loaded a machine plan for a 3D printer. And then makers write workflows, which control the simulation, move things around. In this case, we're 3D printing the first 2 layers of just a basic cube. And finally, makers can browse and apply rules of thumb, which either filter the list of machines based on the requirements that they need, or apply safety checks to their workflow code down here. So that's cool. I've shown Taxon, but now we can return to our original question, which is, which machines can even fit my model? And now we could take the approach where we implement this sort of like one-off feature to solve this in our user interface, but we don't want to stop there, and that's because the maker community is really vast and is growing every day, and we cannot possibly anticipate all the ways that different people are going to want to narrow down the best machine for their needs. Instead, Taxon's strength is that with its programmatic foundation, it lets makers write and share their own rules of thumb for selecting and then using machines. So specifically, there are 2 kinds of rule of thumb. First, filtering rules of thumb narrow down the database of machines to only show machines that satisfy certain requirements, in our example being able to print a model of a given size. And second, action rules of thumb apply checks to the machine simulation as a maker is stepping through that workflow to ensure certain properties, like making sure that the pick-and-place machine has the correctly sized needle to pick up a tiny PCB component. And in particular, catching issues early is super important, because with physical fabrication, any sort of runtime errors mean wasted material. And so here's a reference implementation for filtering a machine based on, is it large enough to print a given model? And this implementation is in JavaScript. So any filtering rule of thumb is a function that takes a machine and possibly a value entered by the maker through the user interface called depth value here. And so in this example, we would first parse the input just to get as numbers the minimum height, width, and length of a model. For example, this familiar low poly Pikachu. And then we want to look at each possible machine's work envelope. And the work envelope is the total volume in which the machine's tool can move. And that kind of defines how big of a model it can print. And so we would only return true if the work envelope's dimensions is greater than or equal to the minimum dimensions given for the model. And so that would filter out all but one machine, the Ultimaker S5 in this example. So syntax aside, the point of all this is that we're able to take this kind of informal knowledge that maybe a couple people knew, and would be able to kind of programatize it and make it accessible to and extensible by all makers. So filtering 3D printers is just one example, but Taxon provides an infrastructure for representing all sorts of different kind of wacky machines and rules of thumb. And to learn more, please see our paper where we investigate several challenges in representing these experimental machines and workflows. And so Taxon, again, applies the safety and extensibility of programming to hands-on making. And our next step is to move Taxon beyond kind of this web simulation into physical settings. In the meantime, I'd like to say thanks to my collaborators and also to the Alfred Sloan Foundation, which funded this work. And finally, I'm looking for collaborators right now, especially undergraduates, if you want to work with me on Taxon. So please reach out if you're interested. And thanks for listening, and happy to take questions.
Okay, any questions for Jasper? And please don't forget, folks in TV land, we also have the chat up here. Stephen.
So I'm curious, Jasper. Rule of thumb. When someone says something is a rule of thumb, they usually don't mean that it's an ironclad guarantee. So what kind of guarantees are you making with your rules of thumb?
Yeah, so the question is like, I guess over the choice, like rules of thumb, why is it called that? Is it an ironclad guarantee or not? And like what sort of things might rules of thumb entail? Yeah, so the whole idea with the rule of thumb is you might consider it similar to like a linter, which suggests, oh, this is like the style you might want to have in your program. So it would just check like you might want to use like spaces instead of tabs or something. And so an example here is like, if the example we saw is if you're printing something, you would want to make sure the machine is big enough. Or another example, I guess, is if you're printing a very tall object, because a 3D printer typically prints layers, you'd want to make sure that you don't have a printer with like a moving bed, because then as it gets, as the object gets taller, it could be less precise at the top. So these are examples, and people don't have to follow them. They can just use them or turn them off. Yeah. Thanks. Mm-hmm. Oh, wow. So.
Edward. I guess this kind of reminds me of like those websites that you can go to for when you're building a PC that have sort of different parts that will or will not fit with each other. And I think like one of the uses of those sites is like looking at different users' sort of use cases and sort of forking off of those. So I was wondering to what extent this would support something like that, or to what extent you're considering like the, I guess like the social dynamic in which this is like going to be deployed.
Definitely. So my understanding is like, to what extent are we thinking about kind of like the user's needs first? That's a great question. So we kind of wanted to start with this foundation of just like, how do you even describe a machine, which is super hard to do generally, and then how does a machine work and what can a machine do? The next logical step is to say, what do you want to make at all? And then translate that to machines. But we haven't gotten there yet, but that's definitely our next step.
Andres.
I guess my question is, when I guess the makers would start with a workflow that they want to, the thing they want to print, is the workflow language kind of already well defined? And then can you, from that workflow, provide like a list of the best machines that you can use from that?
Yeah.
Is that how it works?
Yeah, so the question is are workflows defined already, and could you look at a workflow and then recommend machines? I'll answer the second question first, which is you could do that. You could say, oh, I see you're using a lot of print commands. You might want to consider a 3D printer. So that could be like a basic kind of doing some program analysis and then filter the list of machines based on that. So we could do that. To answer the first question, there's no notion of a workflow at all, really. We just kind of have, our lab group has kind of coined this term and try to make people use it. There is a language called G-code, which has been around since 1950. And this is very low level, just like how do we move from point A to point B and how do we do very specific machine settings. So that's a new thing we're thinking about as workflows.
I think we have one more question here in the back.
Can rules of thumb, can they contradict each other? Or is there some kind of hierarchy of knowledge or ontology you're thinking of? Like, are they user-defined?
Yeah, that's a great question. Is like how are rules of thumb kind of structured, and like can they contradict each other? And so this is one of our kind of unanswered or like things we need to think about more. So far we haven't really defined what happens. So in the case of a filtering rule of thumb, if they conflicted, then you would just see an empty set. And yeah, right now just having like a kind of super long list of these rules is very difficult to use from a user perspective. But I think our first step was like they exist at all, and then we can kind of develop this hierarchy or this way of presenting them to people next. But that is a good point. We haven't thought super closely about that yet.
Okay, let's go ahead and thank Jasper once more. Thanks again, Jasper. And we'll see if we have, if more questions are brewing in your mind and we have time at the end, maybe we can do a little final Q&A. But up next, we have the wonderful Martin, who is one of the department's resident tea experts. So heads up, if you have any tea questions, make sure to hit Martin up. But that's not his research, as fun as that would be. Martin's actually going to tell us about accumulation analysis. So please, Martin, take it away.
Thanks, Zach. As Zach said, I'm going to talk today about my work on accumulation analysis. And accumulation analysis is a special case of a classic program analysis called a type state analysis. And so I'm going to start out this talk by giving you some ideas about type state analysis, what it is, and why people have been interested in it. But first, I want to sort of spoil why we care about accumulation analysis, what the nice thing about it is going to be, which is that it's going to be a lot faster. It's going to be able to express some of the kinds of type state analyses that people are interested in. Not all of them, but some. And the ones that it is able to express, it's going to be much, much faster. And so this is going to make verification a lot more tractable. So it's going to be very nice for users. And the key reason here is that no aliasing analysis is going to be required for soundness. And an alias analysis is another classic program analysis, and it's well known to be very expensive. It's a very active area of research. So I'll explain why this is true later on in the talk, but I just want to sort of give you that right now to know what to look out for. So the talk will be basically in 3 parts. First, what is type state? I'll go into it a bit. Then, what is accumulation? How is it different? And why is it sound? And finally, what kind of things can we do with it? And I'll give you some examples of some of our recent work applying it. So first, type state analysis. So a type state analysis, as I said, is a pretty classic program analysis approach. And what's done in a type state analysis is that for a particular type, a finite state machine is created by the end user as a specification. So this example is for a file object. And the file object can be opened, and then once it's open, it can be read. And once when it's open, it can also be closed. And then you can see that there's this big red X. That's the error state. And a type state analysis's goal is to tell the user if their program could lead to the finite state machine reaching that big X. Right? So it's a verification approach that is basically trying to tell the user whether they violate their finite state machine specification. So for example, we have a file program like this one, where we open it and then we close it and then we read it afterwards, which, as you might imagine, is not a good idea. The way that this will work is first, at the first program point, we'll initialize this finite state machine. In the analysis, it will track F, and you can see it starts closed. When open is called, it'll be opened. When close is called, it moves back to the closed state. And then when read is called, it moves down into the error state here, following that read edge, and issues an error. This is all great. But I mentioned earlier that aliasing is a really important part of keeping track of type states as well. And I want to show an example of why that is. And this is going to be the expensive part of doing type state analysis. So consider instead this other similar program, and suppose that the type state analysis has no notion of aliasing, and therefore doesn't know that G and F are secretly the same file. So first, once again, we'll start with F closed. It'll be opened. And then this aliasing occurs, and so now we have 2 type states. We have F and we have G. They're in orange. And then F is closed, so it moves there. And if the type state analysis doesn't know that these are the same, then G stays here in this open state, and this call to read is permitted. Right? But you and I, looking at this program, can tell that this is actually a bad idea. Right? We've missed an error. That's bad. And this is what we, in programming languages, would call a false negative. And this is very bad because we want to verify that the user's program is correct. So because of things like this, in the general case, when you do a type state analysis, you need to have this aliasing information. And so you have to keep the FSMs of all the aliases in sync. So practically, what do people do? So there's sort of 2 approaches. One, just ignore aliasing and allow unsoundness, become a bug finder rather than a verification tool. Some of my colleagues at AWS recently published a paper about how they did this and deployed it at scale, which is pretty cool, but it's not sound. It can't give you a guarantee about your program. It can only find some bugs. And the other choice is a whole program may alias analysis. Again, active area of research, very expensive. You generally don't want to do this if you want to get results in the next hour. Okay, so now I want to talk about my work in developing accumulation analyses, which is a special case of type state. So an accumulation analysis is a type state analysis whose state representation here is a monotonically increasing set. And I have a formal definition here, which you should not read. And I want to just do this by example, rather, to give the idea of what's going on here. So an example of one of the sorts of type state analyses that one might want to do with an accumulation analysis is object initialization. So before you use an object of some type T, set the F and G fields to some sensible values. And so suppose that we have a piece of code, right? We have some T, and we have T.F and T.G, and then some use, right? So the accumulation analysis, what it's going to be keeping track of, rather than a direct FSM, it's going to keep track of just a set of which fields have actually been initialized. So at the start, it's the empty set, Then after t.f is assigned, the set will be the set containing f, then the set containing f and g, and then we'll be able to validate that this use is okay. Right? But if something happened in the middle there, the analysis is able to forget things, and it will still work out. Yeah. So why? Well, because it's sound without alias reasoning. So as I mentioned, in traditional type state, aliasing allows type states to sort of get out of sync. Right? They can, you can have two that are in different places. But because accumulation only has enabling transitions, it's sort of building up to the point where it's okay to do something, and it's never possible to go back once you're there. The analysis itself can always say, all right, I knew all this stuff, but something bad has happened, and I'm forgetting it because it might not be true anymore. And it's still sound while doing that. You can't open then close and sort of go back and forth. So files, as I mentioned, the file example I gave at the beginning is an example of a type state analysis that is not an accumulation analysis. It requires aliasing. But this object initialization is not. OK, so what can we do? So first, the first example is going to be initialization, like I just showed. And I want to emphasize here that not every type state analysis is going to be amenable to this. So we've been doing some work now on a literature survey looking at what people have done with type state. And we think it's probably about between 20 and 50% of the kinds of things that people want to do actually are accumulation. But we still think that's a big savings. OK, some important ones are initialization. The type state for initialization, the example that I showed on an earlier slide, looks kind of like this. So you can see the set f and set g. And then using too early there is in the middle. And I want to emphasize that this sort of all flows in one direction. Right? That sort of gives you that type states for accumulation analyses usually look a lot like this. And yeah, like I said, this is how it's actually implemented. This is the example I showed from before. With this, we also did a user study with some programmers. So we implemented this, and we asked them to add a required field to a new builder, a new required field to a builder. It's a particular initialization pattern that's popular in Java. And we found that with our tooling, they were 50% more likely to be successful, and about 50% faster. So programmers like having the analysis be quick and tell them when they're wrong. Another example of something that we can do with accumulation that people had thought you might need a full type state analysis for before is resource leaks. So the type state for resource leaks looks something like this. And our key insight here was treating going out of scope as a transition. So sort of, if you know about type state, that's important, but we can just move on. And we built this as well. And our tool is this one in blue here. And this is compared to some other extant approaches. So you can see that only our tool has good recall. That's because it's sound. The others are quite poor. Precision is about the same, and ours is very fast. So that's it. Type state requires alias reasoning for soundness. It's a cool, well-studied approach, but hasn't been deployed very much because it's very expensive. Accumulation does not require that, so it's a lot faster, so it's a lot easier to deploy. And it allows us to soundly verify some important type state-like properties. And I also want to thank my awesome collaborators who've worked with me on this work. Thanks.
Thanks, Mark. OK, I know everybody's had bugs with locks or files or something. Any questions in the audience for Martin? Oh, Remy.
Yeah, so is it possible to take a type state analysis and automatically check if it's expressible in accumulation, and then compile it into a Bayesian analysis ATS?
Great question, Bernie. So we're working on doing that right now. We don't have a proof yet that allows you to do this, but we think we're close, and hopefully then we'll be able to automate it. So that's actually literally what I'm working on right now. Yeah, because it would be amazing.
So we also do have a question from the Zoom chat. The great DJG, who some know as Dan Grossman, asks, conventional data flow analyses also have this kind of accumulation property, right? Because you force things to go up the lattice. So,
yeah.
So what's the relationship between this type state perspective and doing sort of the type system approach and the data flow analysis perspective?
That's a great question. So I think the best way to think of it is that accumulation is exactly the type state properties that are expressible as data flow. All right. So I mean, our implementation is basically data flow. It's as a type system. Yeah, I think that's the right way to think of it.
I wonder if the error messages that you can pull out of a type state analysis are perhaps nicer. I don't know. Something to think about.
Good question. Don't know.
Okay, friends, any more questions? I realize we are getting a little bit tight on time. I want to make sure we give Gus a full shot. Okay, let's thank Martin once more. And last but certainly not least, Gus, who has become an avid woodworker during the pandemic. He particularly enjoys working with cherry and walnut. Anyways, Gus is going to tell us about how we can overcome some of the challenges in applying term rewriting systems to reason about tensor workloads. So please, Gus, take it away.
Great. Thanks so much, Zach. I appreciate it. Okay, so hi, everybody. Like Zach said, my name's Gus. I'm going to just talk a little bit about a language that myself and some colleagues in the Pulse lab and in the sample lab built for rewriting over tensor kernels and optimizing over tensor kernels. So before we get started, I want to give a brief example of what term rewriting even is, if people don't understand what term rewriting is, if they haven't heard of that before. So imagine we have a really simple program. So it looks like just a mathematical expression, right? It's a simple program, a times 2 divided by 2. And after staring at this for a bit, we should realize that this can be simplified to the even simpler program, a. So if we were building a compiler for simple programs like this, we'd want to make sure that our compiler understood how to make this transformation. So how do we transform from this original program down to this simplified one? How would we implement this optimization? Well, a really common framework to use for doing these types of optimizations is something called term rewriting, where you build up complex optimizations by applying smaller optimizations to sub-expressions of your program. So for example, we might have a program rewrite that matches on this pattern, x times y divided by z, and it reassociates the division and the multiplication, and that gives us this expression. Then we might have a rewrite that takes x divided by x and just simplifies it down to 1, and then that would give us this expression, a times 1. And then finally, we'd have another straightforward rewrite that matches on x times 1, and it rewrites that to just x, and that gives us our simplified expression. So as you can see, term rewriting is simple, and yet it's powerful. And unsurprisingly, it's a very fundamental tool in many modern compilers. And modern term rewriting engines such as Egg, which is actually developed here at Pulse by Max, they're very powerful. And they've been used to great success in a number of domains, such as CAD program simplification and floating point optimization. So I work on machine learning compilers specifically. So when Max and everybody in the lab started getting excited about term rewriting, my natural question was, can we apply term rewriting, and more specifically, can we apply Egg on ML tensor kernels? And if that just sounded like 3 buzzwords in a row, you're right. So let's get a little glossary here. What's a tensor? A tensor is just a multi-dimensional array. It's just a matrix. It's just a vector. Vector is a one-dimensional tensor. Matrix is a two-dimensional tensor. Then you can increase the dimensions as you go. Just a multi-dimensional array. Fancy word for that. A kernel is just a highly optimized, highly used function. And so a tensor kernel, when you put them together, that's something like matrix multiplication, which is used all of the time in machine learning. And so we've hyper-optimized it. So that's all I mean by tensor kernel. So after surveying the landscape of tensor languages, of languages that operate over and represent tensor programs, I quickly discovered that current tensor languages are not really amenable to term rewriting and are not really amenable to being optimized using Egg. So in our case, what are we looking for in a language? Well, we're looking for a language that is both pure, meaning simply it doesn't have any side effects. We can kind of reason about the program like it's just a simple mathematical expression. And also that it's low level, which means that the inner workings of the program itself are exposed and represented, because if we can't see the inner workings of the tensor kernel, how can we really do any optimizations? So we're looking for something that's in this Goldilocks zone, and we didn't really find any languages that really fit that. And so we designed Glenside, which is a pure and low-level tensor language. So let's talk a bit about Glenside. So the outline for the rest of this talk, first I'm going to talk about matrix multiplication. We're going to step through how we implement matrix multiplication in a low-level and pure way, and that's going to be kind of our motivating example. And then we'll use what we learned from that experience to define Glenside's core abstraction, which we call the access pattern. and the rest of Glenside. We'll use it to define the rest of Glenside as well. And then we'll hint at some case studies about why Glenside is actually useful and why it's neat. So let's hop in and kind of explore matrix multiplication. So remember, what we're trying to do is implement matrix multiplication in a low-level and pure way. So just to remind ourselves, the algorithm, one way to describe the algorithm for matrix multiplication is given matrices A and B, pair each row of A with each column of B, then you compute the dot products of those row-column pairs, and then you arrange the results back into a matrix. So that simple English description immediately suggests a pretty good, pure, low-level implementation of matrix multiplication. So we'll step through it visually. The first thing that we do, so we have A on the left here, we have B on the right, both matrices, two-dimensional tensors. We're going to view matrix A as a list of its rows. We're going to view matrix B as a list of its columns. Then we're going to take the Cartesian product of the rows of A with the columns of B. And if you haven't heard of Cartesian product before, it's just an operator over two lists. It basically gives you every item from list A paired with every item from list B. So the result of the Cartesian product is every row from A paired with every column from B. Then we're going to map the dot product operator over this list of row-column pairs. And so map is just the traditional functional definition of map. We take an operator and we apply it to everything in the list. And that gives us this list of scalars. But there's a problem here. So while the values in this list may be correct, we're missing something key. So a two-dimensional matrix times a two-dimensional matrix should produce a two-dimensional matrix. And what we get out is a flat list of scalars. And so we've lost the shape. We don't actually have the shape of the output tensor, which is a key piece of information. So let's step back in time and understand where that shape information got lost. So by the time we're mapping the dot product operator over our list, we have already lost the shape information. It's just a flat list of row-column pairs. And that's also the case in the step before. But at this step, just before we apply the Cartesian product operator, we have all of the original shape information. That is, we have A as a two-dimensional matrix, and we have B as a two-dimensional matrix. We have A as a list of rows, B as a list of columns. So then when so shape information is present here, but then when we step forward, shape information is now lost at this stage. So it seems that Cartesian product is somehow destroying our shape information. So what we do is we introduce a new Cartesian product operator. And this Cartesian product operator actually preserves shape information. So now the Cartesian product of the three rows of A with the two columns of B is actually a 3x2 matrix of pairs. It's not just a flat list of pairs. But now when we try to map our dot product operator over this new list, we run into another issue, which is that map just maps dot product one level deep. And it tries to map the operator over the wrong dimension. So we also introduce a new map2D operator. And this map2D knows to map dot product two levels deep, correctly mapping the dot product onto the row-column pairs. And finally, we get out the thing we expected, which is a two-dimensional matrix. So what actually happened here? What happened in this example? What can we learn from this? Well, Cartesian product 2D and map2D both hard code which dimensions are iterated over and which dimensions are computed on. But if the shapes of A and B change, we'll need entirely new operators, something like map3D. So can we encode this information, and by this information I mean the dimensions that are iterated over and the dimensions that are computed on, can we encode this directly in the tensors themselves? And so unsurprisingly, the answer to this question is yes, and this is exactly what access patterns are designed to do. So let's learn about what access patterns are. So access patterns, you can think of them as basically a view on top of a tensor. They just add a bit more information on top of the traditional tensor. So whereas a tensor is usually defined by a tuple of integers called a shape, so in this case 3, 4, indicating that this tensor has three rows and 4 columns, an access pattern is defined by a pair of tuples, where the first tuple holds what's called the access dimensions, which are the dimensions that are iterated over, and the second tuple holds the compute dimensions, which are the dimensions that are computed on. And concatenating those two tuples together gives you the shape of the underlying tensor, in this case, 3, 4. So an axis pattern simply represents a view over a tensor. That's all it is. And that view is actually conveying how the algorithm is processing this tensor. So for example, this axis pattern is viewing our 3, 4 shaped tensor as a 3-length vector of 4-length vectors. But if we shift the dimensions of the axis pattern over, we can view the same tensor as a 3, 4 shaped tensor of scalars. And if we shift it in the other direction, we can view it as a scalar-shaped tensor in which that quote-unquote scalar or single element is a 3, 4 shaped tensor. So each of these views is a valid view over the tensor that might be useful in a different algorithm. And so now we can redefine a bunch of list and tensor operators using these axis pattern semantics, and that gives us the Glenside language. You don't have to read this table underneath, it's all in the paper, but know that Glenside is basically just a bunch of common operators redefined over these axis patterns. And so now, really quickly, one slide on a case study of where Glenside gets used. So now imagine we have a hardware designer who's designed a piece of hardware for machine learning, accelerating machine learning computation. And now with Glenside, our hardware designer, she can actually write a term rewriting rule which matches, so this is our piece of hardware, she can write a term rewriting rule which matches on computations that her hardware can compute and can actually rewrite them directly to invocations of her hardware. And now building a compiler for her custom hardware can be potentially as simple as writing a single rewrite rule for Glenside. So that's just a teaser of some of the case studies that we showed in our paper. I also have a longer talk on this. Glenside is also an actively maintained Rust library, so if you want to pull it down and check it out, feel free. Thanks to everybody who helped with this work. Thanks to my lab. Thanks to our funding agencies. And happy to take any questions.
Okay, any questions for Gus? Term rewriting on tensors. Andres, killing it today.
Yeah, have you taken the next step of actually integrating the X into the inside?
What
How does that work? Yeah, like rewrite rules built on Egg, as I understand it.
Oh yeah, so actually, Glenside really came out of, it was built on top of Egg, basically. So Egg, we built Glenside to use Egg, and we've actually, so far, we've used it to do a bunch of interesting things. So that case study that I showed at the end, where we're doing that rewrite, where we basically have a rewrite rule that says, here's what my hardware computes. Now rewrite my program to an invocation that goes to my hardware. We did that using Egg. So that's done using Egg. We're working on something now, which is, we're calling flexible matching, which is essentially using hardware that was written for another purpose, and using some simple rewrite rules in Egg to kind of expose that, oh, we can actually map this program that's unrelated to this hardware to this hardware. So that's also done using Egg. So really, Glenside is really made for Egg in a way, but it's useful for any kind of term rewriting that you want to do over tensor programs.
Steven.
So, Gus, I just came up with this right now. I promise I'm not trying to trick you. You emphasized purity in the design of Glenside, and it makes sense why purity is useful. But a lot of hardware is stateful in nasty ways. Do you have any ideas for how to deal with that?
Yeah, so Zach and I were just talking about this. This is kind of my first foray into the realm of purity, and I'm sure that purity causes a lot of problems because, hardware accelerators obviously aren't pure. But I mean, a CPU is not pure, and yet we still get, something like Haskell compiling and running just fine. So I don't think that, I think we're going to definitely run into these issues, but I'm really, I'm crossing my fingers that we are going to be able to solve those issues using things that already exist in the compiler's literature. People here don't know this, but I wasn't originally a PL person or a compilers person, so a lot of this stuff is truly new to me, and I've really just been relying on the fact that the problems that I know are going to come up, which is, Stephen raised a great point. I think, hardware not being pure, but this language being pure, that's a great point. I'm mostly relying on the fact that there's going to be stuff in the literature to help us solve this. So it's a really good question. I'm not exactly sure on how we're going to do it, but I strongly suspect there's going to be existing methods to help us fix those problems.
And I think we'll have a last question from Lancelot.
Yeah, so I guess is one of the main problems that you're trying to solve that you want something computed, but your memory is arranged differently than what the algorithm wants, like what the function wants?
So that's actually, so that is something that we can handle here, and that's actually something that we have handled in the past. Really, the initial intent here was we didn't even have a specific intent like that. We didn't say like, here's my problem, and here's what I want to solve. We were mostly just like, what neat optimizations can we do if we put tensor program optimization into egg? But one of the things that we actually found we were able to do, and it's not in this slide deck because it's a little too complex, but there's a kind of a classic transformation in the world of accelerators in which you actually reformat your data, like you're talking about, the layout of your data, and you duplicate a little bit of your data, and you're able to map this kernel called 2D convolution into a matrix multiplication, which is something that's used all the time in the world of accelerators. And it's something that Glenside can actually discover naturally with 1 or 2 rewrites, which is really interesting and was a neat and very affirming discovery.
Okay, so it more like tells you that you need to do that or something. Like, it's not trying to tackle the actual memory rearrangement, sort of.
Well, so it'll tell you how you need to rearrange your memory to take advantage of this optimization. Yeah.
Okay, friends, I think we're going to go ahead and call it there. Let's thank all the speakers one last time. And also, please make sure to thank everyone on the production crew. It's quite an ordeal to run this in a hybrid fashion. So many thanks to the folks in the back and Kay and everyone. Super, super appreciate that. And yeah, make sure to come next week to hear about some really exciting comp bio and computational medicine work from Suin's Ames group. It's going to be super, super exciting. Stay safe, folks, and we'll see you next week.